Okay, so what if I told you that the entire AI revolution, I'm talking about everything from ChatGPT to these tools that feel like they're straight out of science fiction, is all built on a foundation that is, frankly, ridiculously simple. It's kind of the biggest open secret in tech, hiding right there in plain sight. Seriously, that's it. That is the whole game. At its absolute fundamental core, the most sophisticated artificial intelligence ever built by humanity is just playing an endless game of guess the next word. Everything else, all the complexity, all the stuff that looks like real intelligence, it all flows from this one simple task.
And the crazy part is, this isn't even a new idea. We're talking about a concept from 1951, from the father of information theory, Claude Shannon. The basic task is really just autocomplete. Think about the autocomplete on your phone. Now imagine that on a godlike scale. What's changed isn't the idea. It's the sheer, almost unimaginable scale at which we're now playing this game.
So let's actually see how this works. The model gets a starting word, A. It looks at all the possibilities and predicts the most likely next one, robot. Now this is the really crucial part. That new phrase, a robot, becomes the new input. The model is literally feeding its own output back into itself. From that new context, it predicts can. Then from a robot can, it predicts not. This is what's called an autoregressive process. It's building on itself, creating complex thoughts one single word at a time.
Okay, so this is the big question, right? How does this incredibly simple prediction game create models that can write poetry, that can debug computer code, and even seem to reason? Well, the answer is one of the most fundamental and honestly controversial principles in all of modern AI: scale. And this is where things get a little mind-bending. The theory is that when you force a model to get exceptionally good at predicting the next word, across trillions of examples from the internet, it can't just memorize sentences. To win the game, it's forced to build an internal model of how the world works. Grammar, facts, logic, cause and effect. Intelligence isn't being designed, it's being learned through this massive scale pattern matching.
This whole concept is known as scaling laws, and the idea is pretty wild. For a long time, making AI smarter wasn't some deep research mystery. It was basically a predictable engineering problem. You want better performance? You just add more data, you make the model bigger with more parameters, and you throw a ton more computers at it. The improvements would just follow this predictable, almost mechanical curve.
And when we say scale, the numbers are just staggering. GPT-3 was trained on 500 billion tokens, and that was considered absolutely massive at the time. Then came models like Llama 2 at 1.4 trillion. And now you have models like Gemma being trained on 6 trillion tokens. That is an amount of text a human couldn't even read in 1,000 lifetimes.
So the takeaway here is crucial. Scale isn't just one ingredient in the recipe. For a long time, it has been the main ingredient. It's the brute force that unlocks all of these incredible abilities from that simple little game of guessing the next word.
But here's where the story takes a turn and gets truly mysterious. Because at these massive, massive scales, something really unexpected begins to happen. Something that wasn't explicitly programmed into the model starts to, emerge.
Let's look at a simple test. Researchers gave one of these huge models. It's a basic math problem. Any kid in grade school could solve it. So a super powerful AI that's been trained on a huge chunk of the internet, this should be a piece of cake, right?
Nope. It fails, and it fails confidently. The answer, of course, should be 7, but the model spits out 10. This is the moment where you'd think, okay, this whole intelligence from scaling thing is falling apart. The model can write a beautiful essay, but it can't do simple math? What is going on?
Well, here's where it gets fascinating. The fix isn't to retrain the model or change its code. The fix is to change just 5 words in the prompt. Instead of just asking for the final answer, you add a little magic phrase. Let's think step by step. And just like that, it gets it right. By prompting it to basically show its work, it correctly follows the logic one step at a time. It lays it all out. Jack starts with 7, minus 2 is 5, plus 5 is 10, and finally, minus 3 is 7. The ability was in there the whole time, just hidden, latent, waiting for the right prompt to unlock. So this is what we mean by emergence, this ability to reason. It just appears from the scaled-up task of predicting words. This is the ghost in the machine. It was never programmed to do math. It was programmed to predict text. But in learning to do that perfectly, it somehow picked up a skill that looks an awful lot like reasoning. And this just sparks this huge debate. Is it actually thinking, or is it just an incredibly sophisticated mimic of what thinking looks like in text? Now, this emergent power is incredible, but it creates a massive problem. A raw model, one that's only trained to predict the next word based on the internet, has zero concept of truth or safety or human values. And with great power comes great risk. That power has to be aligned.
Yeah, an unaligned model is basically a wild beast. It might ignore what you ask it to do, it can generate harmful content that it learned from the dark corners of the web, or it might just make stuff up, what we call hallucinating, and present it as solid fact. The raw, pre-trained model is powerful for sure, but it's not safe or reliably helpful.
So how do you tame that beast? Well, it's a critical three-step process. First, you show it the rulebook. You give it thousands of high-quality examples of how to follow instructions correctly. Second, you hire human judges. These people look at different AI answers and rank them from best to worst. A totally separate AI, called a reward model, is trained to predict what the humans will like. And finally, you train the original model to always try and please that judge, basically teaching it to chase a high score for being helpful and harmless.
And here's a perfect example of what that looks like. You ask how to live more sustainably. One answer is extreme: go off-grid. The other is more practical: support local farms. A human rater decides the practical answer is more helpful. The reward model learns this preference, and the LLM is then trained to produce more answers like the one on the right.
Okay, so we've got this massively scaled, surprisingly capable, and now carefully aligned model. How do we, the actual users, get to interact with it and control all of that power?
Well, it all comes down to the prompt. Prompting is our control panel. It's how we steer the ship. It's how we leverage all of that pre-training, all that scaling, and all that alignment work. A really well-crafted prompt, just like that let's think step-by-step example, is how we tell the model which of its vast capabilities we need it to use.
And when you hit enter, a two-phase process called inference kicks off. The first phase is called pre-filling. This is where the model just digests your entire prompt all at once to build a rich understanding of the context. Then it switches to decoding, and it goes right back to that simple game we started with, generating the response one single word at a time. You can see it right here in action. The prompt, "the cat is sleeping," gets processed all at once. Then decoding begins. It predicts the word peacefully. Now the entire phrase, "the cat is sleeping peacefully," becomes the new context. From there, it predicts a period. Finally, it predicts a special stop token, and the whole thing is done. To us, it happens in a flash, but behind the scenes, it's this incredibly meticulous step-by-step construction.
And that brings us right back to where we started, but with a much, much deeper question. We've seen how a simple prediction game, when scaled to an astronomical size, can give rise to abilities that look just like reasoning. But if complex intelligence can just emerge from a simple brute force task, what does that say about our own intelligence? Is it also just a product of scale and prediction? Are we just a ghost in the biological machine? That's the profound question these models are forcing all of us to ask.